Picture this: a night sky so clear, so untouched by modern light, that every star burns with an almost supernatural brilliance. This was the world of ancient astronomers, who gazed upward, not with telescopes or satellites, but with nothing more than their eyes, their patience, and an unshakable determination to understand the cosmos. What they achieved is nothing short of miraculous. Civilizations like the Babylonians, the Mayans, and the Egyptians didn't just observe the heavens. They mapped them with a precision that still leaves scientists in awe today. How did they do it? What cosmic secrets did they uncover? And why does their knowledge still matter in our age of space exploration and advanced technology? That's the mystery we're about to unravel. Think about the sheer audacity of their task. Without calculators, without even the basic tools we take for granted, these ancient stargazers tracked the movements of planets, predicted eclipses, and even documented comets that streaked across the sky centuries ago. Their records weren't just scribbles on stone or parchment. They were intricate mathematical masterpieces, encoding celestial patterns with a sophistication we're only now beginning to fully appreciate. Some of their discoveries were so accurate that modern astronomers have used them to verify events that happened thousands of years in the past. It's as if they left us a cosmic time capsule waiting to be decoded. But here's the most fascinating part. Their wisdom wasn't just about the stars. It was woven into the very fabric of their cultures, their religions, their daily lives. The pyramids of Egypt align with constellations. The Mayan calendar, often misunderstood, was a breathtakingly precise system for tracking celestial cycles. The Babylonians left behind clay tablets that reveal their ability to predict lunar eclipses down to the hour. These weren't just scientific achievements, they were acts of reverence, a dialogue between humanity and the universe. And that's what makes this journey so compelling. We're not just exploring ancient astronomy, we're rediscovering a lost connection to the cosmos, one that might just hold clues to mysteries we're still trying to solve. So let's step into their world, trace their footsteps across the night sky, and uncover the astronomical wisdom they left behind. The stars are waiting. Long before the invention of telescopes or even the most basic optical tools, ancient civilizations turned their gaze upward with nothing but patience and persistence. They didn't just watch the stars, they studied them, mapped them, and built entire monuments to mirror the heavens. Take Stonehenge, for example. Those massive stones weren't just arranged for ceremony or spectacle. They were a precision instrument, marking the summer and winter solstices with eerie accuracy. On the longest and shortest days of the year, sunlight pierces through the structure in perfect alignment, a testament to the builder's deep understanding of Earth's relationship with the sun. But Stonehenge is just one piece of the puzzle. Halfway across the world, the pyramids of Giza stand as another marvel of cosmic engineering. The Great Pyramid's sides align almost perfectly with the four cardinal directions north, south, east, and west, with an error margin so small it rivals modern surveys. Even more astonishing, its air shafts point directly to key stars in the night sky, like Sirius and Orion's belt, suggesting these weren't just tombs but celestial observatories. Imagine the generations of knowledge it took to design something so precise, all without compasses or satellites. Then there's the Mayans, whose obsession with timekeeping led to one of the most sophisticated calendars ever created. Their observatories, like El Caracol in Chichen Itza, were designed with narrow windows that framed Venus at its most critical positions in the sky. They tracked its cycles so meticulously that they could predict its appearances centuries in advance. For them, Venus wasn't just a bright dot, it was a deity, a harbinger of war or fortune, woven into the very fabric of their mythology and daily life. What ties all these cultures together? A relentless dedication to observation. Night after night, year after year, they recorded the movements of the cosmos, noticing patterns invisible to the casual eye. They didn't have the luxury of writing things down in books, so they encoded their knowledge in stone, in architecture, in stories passed down through generations. And here's the most humbling part: their methods were so effective that modern astronomers still reference their records today. When a comet appears or an eclipse darkens the sky, chances are an ancient civilization not only saw it but left us a detailed account. That's the power of their legacy, not just what they knew, but how they chose to preserve it for the future. While we marvel at modern astronomy's high-tech tools, the Babylonians were laying its groundwork over 3,000 years ago with nothing but clay tablets and sharpened reeds. These weren't casual notes, they were meticulous scientific records, etched into wet clay that hardened into permanent archives of the cosmos. Imagine the dedication it took to track the moon's every wobble, Jupiter's looping path, or the slow dance of stars across centuries, all without telescopes or calculators. Their oldest surviving tablets, dating back to around 1800 BC, reveal something extraordinary: a civilization that didn't just watch the sky, but deciphered its rhythms with mathematical precision. One of their most astonishing achievements was eclipse prediction. By recognizing a repeating pattern now known as the Saros cycle, a cycle of approximately 18 years between similar eclipses, they could forecast lunar eclipses down to the hour. Their calculations were so reliable that modern researchers have compared their records with NASA's retroactive models and found near-perfect matches. Think about that for a moment. Using only naked eye observations and clay tablets, they unlocked a celestial secret that still holds up against supercomputers. But their brilliance didn't stop there. The Babylonians also mapped the zodiac, dividing the sky into 12 equal sections, a system so enduring it shapes astrology today, even if its original purpose was purely scientific. They tracked Venus so closely that their data helped 20th century astronomers refine the planet's orbital timeline, and their star catalogues, listing constellations and planetary movements, became the backbone for later Greek astronomers like Ptolemy, who built upon their work. What's truly humbling is realizing how much they accomplished without any of our modern advantages. No paper, no printing presses, just fragile clay preserved by chance, waiting millennia for us to rediscover their genius. These tablets weren't just ancient astronomy, they were humanity's first steps toward mastering the universe's clockwork, and the most poignant part: we're still learning from them. When a newly discovered tablet sheds light on a forgotten eclipse or planetary alignment, it's not just history, it's a conversation across time, a reminder that curiosity and perseverance are the truest tools of discovery. The Mayans didn't just measure time, they mastered it in ways that still baffle modern scholars. At the heart of their cosmic understanding lay the long count calendar, a system so vast it spanned over 5,000 years, tracking epochs with mathematical precision. Unlike our linear Gregorian calendar, the long count wove time into cycles within cycles, like celestial gears turning in perfect sync. But here's what's truly astonishing: their calculations weren't just about marking days. They predicted planetary alignments, eclipses, and even the rare transits of Venus with an accuracy that rivals today's astronomical software. Take the Dresden Codex, one of the few surviving Mayan manuscripts. Buried within its fragile pages are Venus tables so detailed they could forecast the planet's appearances, as both morning and evening star for centuries into the future. Venus wasn't just a point of light to the Mayans. It was the god Kukulkan, a deity whose movements dictated war, harvest, and royal ceremonies. Their ability to predict its cycles wasn't just science, it was divine diplomacy, a way to align human affairs with the heavens. And they did it without telescopes, relying instead on generations of naked eye observations etched into bark paper and stucco walls. Yet their genius didn't stop at Venus. The Mayans also tracked the moon's wobbles with a precision that allowed them to correct their lunar calendar by a fraction of a day per century. Their solar calendar, the Hob, aligned so closely with Earth's orbit that it drifted by just one day every 52 years. Imagine the patience required to refine such systems over centuries, watching the skies night after night, passing knowledge down like a sacred torch. What's most striking, though, is how deeply astronomy was woven into their world. Temples like El Castillo at Chichen Itza weren't just buildings, they were cosmic mirrors. During equinoxes, sunlight slithers down the pyramid steps as a serpent of shadow, a literal descent of Kukulkan. Even their cities were laid out to mirror constellations, turning urban centers into terrestrial maps of the stars. For the Mayans, time wasn't abstract, it was alive, a force as tangible as stone or rain. And that's the real lesson they left us. Their calendars weren't just tools. They were bridges between earth and sky, proof that humanity's oldest questions about the universe can be answered not just with technology, but with patience, observation, and an unshakable belief in the patterns hidden in plain sight. The Egyptians didn't just build pyramids, they engineered them as celestial timekeepers, stone monuments whispering secrets of the stars. Take the Great Pyramid of Giza, its 3 chambers aligning with the 3 stars of Orion's belt with a precision that defies coincidence. But this wasn't just symbolic, it was a deliberate act of cosmic cartography. The pyramid's southern shaft points directly to Sirius, the brightest star in the night sky, while its northern shaft targets the circumpolar stars which never set below the horizon. To the Egyptians, these stars represented eternal life, and their alignment with the pyramid's passages suggests a belief that the pharaoh's soul would journey through the heavens. This wasn't architecture, it was astronomy carved in stone. Then there's Karnak, the sprawling temple complex where sunlight performs a sacred dance. On the winter solstice, the sun rises at just the right angle to flood the innermost sanctuary with light, illuminating statues of the gods as if awakening them from slumber. The same precision appears at Abu Simbel, where twice a year, on the pharaoh's birthday and coronation day, sunlight pierces 60 meters into the temple to bathe the statues of Ramses II and the gods in golden light. These weren't random effects, they were calculated down to the minute, a testament to the Egyptians' mastery of solar cycles. But their celestial knowledge wasn't just for spectacle, it was survival. Sirius, known as Sopdet to the Egyptians, held the key to their agricultural cycle. When this star first appeared just before dawn, a phenomenon called the heliacal rising, it signaled the imminent flooding of the Nile. These floods were the lifeblood of their civilization, depositing fertile silt that fed their crops. By tracking Sirius, they could predict the floods with astonishing accuracy, turning astronomy into a tool for food security. What's most striking is how seamlessly they merged science and spirituality. Temples weren't just buildings, they were mirrors of the cosmos, designed to align with celestial events that reinforced their myths. The god Osiris was linked to Orion, Isis to Sirius, and the sun god Ra's journey across the sky mirrored the pharaoh's path through the afterlife. This wasn't superstition, it was a holistic understanding of the universe where the practical and the divine were inseparable. So were these alignments accidental? The odds are astronomically low. The precision required to orient structures across hundreds of feet, the consistency with which they tracked stars over centuries, it all points to a civilization that didn't just observe the heavens but conversed with them. Their legacy isn't just in the stones they left behind, but in the realization that the sky was never just a mystery to them. It was a map, a clock, and a sacred text, all written in the language of light. While the Babylonians and Egyptians mapped the heavens with numbers and stone, the Greeks added something revolutionary story. Imagine standing under the Mediterranean sky 2,300 years ago, where every cluster of stars wasn't just a set of coordinates but a character in an epic tale. Orion the hunter forever chasing the Pleiades, Hercules mid-labors, Andromeda chained to her rocky fate. These weren't mere patterns. They were a celestial theater, blending science and myth into a single language of the cosmos. At the heart of this fusion stood pioneers like Hipparchus, whose star catalogue mapped over 850 stars with painstaking accuracy. But here's what's fascinating. Even as he calculated their positions down to fractions of a degree, he worked within a sky already alive with legends passed down from Homer and Hesiod. His science didn't erase the myths, it coexisted with them, as if the Greeks understood that data alone couldn't capture the wonder of the universe. Then there was Ptolemy, whose geocentric model, with Earth as the universe's fixed center, dominated Western thought for 1,400 years. His masterpiece, the Almagest, wasn't just a technical manual. It wove Babylonian eclipse records, Greek geometry, and poetic celestial lore into a system so compelling that even its errors felt sacred. Why did this flawed model endure so long? Because it wasn't just about mechanics. It offered a story of perfect crystalline spheres, of planets moving in divine harmony, a cosmic order that mirrored humanity's place in the grand design. But the real magic lies in how these Greek astronomers bridged two worlds. They didn't dismiss the myths as childish fables. They saw them as another way to decode the universe. When they named constellations after heroes and monsters, they weren't being unscientific. They were creating memory aids, turning the sky into a mnemonic device. Sailors navigating by Polaris weren't just following a star. They were guided by the Phoenician stories of the steadfast guardian. This duality shaped astronomy for millennia. Medieval monks preserving Ptolemy's works didn't just copy his math. They illuminated his texts with zodiac symbols and mythological illustrations. Renaissance scholars like Kepler, while dismantling the geocentric model, still spoke of planetary musica, the music of the spheres, a poetic holdover from Greek cosmic storytelling. Even today, when we call a galaxy Andromeda, we're heirs to that ancient tradition where science and myth aren't rivals but collaborators in humanity's oldest quest to find meaning in the stars. Perhaps that's the Greeks' greatest lesson. They remind us that astronomy isn't just about charting distances or calculating orbits. It's about wonder, the same wonder that made them see not just points of light, but heroes, beasts, and gods dancing across the eternal night. While the Greeks wove myths into their stars, the Chinese turned the heavens into an imperial archive, a celestial ledger where every comet, every exploding star, was dutifully recorded as if the sky itself were reporting to the emperor. Picture astronomers in ancient Loyang, crouched over bamboo slips under the faint glow of oil lamps, inscribing the sudden appearance of a guest star. What we now know was a supernova with the same gravity as a royal decree. Their records stretch back to the Shang dynasty, around 1600 BC, making them the longest continuous astronomical chronicle in human history. But here's what sets them apart. These weren't just observations. They were urgent messages from the cosmos, believed to hold the fate of dynasties in their flickering light. The Dunhuang Star Atlas, painted on paper around the year 700, is a masterpiece of precision. Unlike Western constellations that imagined shapes in the stars, Chinese astronomers mapped the heavens as a bureaucratic grid, dividing the sky into 28 lunar mansions, each a celestial province ruled by its own asterism. The atlas pinpoints over 1,300 stars with an accuracy that would make modern cartographers nod in respect. But look closer, and you'll notice something extraordinary. The stars aren't just dots. They're color-coded, red for prosperity, black for calamity, a visual shorthand tying celestial events directly to earthly fortunes. Take the supernova of 1054, recorded with meticulous detail as a star bursting in the constellation of Taurus. Modern telescopes later identified its remnant as the Crab Nebula, but to Song Dynasty court astronomers, it was an omen demanding interpretation. Was it a warning of peasant uprisings? A sign of heavenly approval for the emperor's latest reforms? Even sunspots, observed through jade filters to protect the eyes, were scrutinized for hidden meanings. One Tang Dynasty report describes them as crows perched on the sun, symbols of discord that sent imperial advisors scrambling to avert misfortune. This fusion of science and divination reached its peak with comets, celestial broomsticks believed to sweep away old regimes. The Mawangdui silk texts, buried in a Han Dynasty tomb around 300 BC, classify comets by their tails. Hooked ones foretold military defeats, straight tails predicted droughts, and branched tails signaled epidemics. When Halley's Comet blazed across the sky in 2040 BC, Chinese scribes noted its appearance coincided with the fall of a warlord, cementing its reputation as a harbinger of upheaval. What's most striking is how seriously these records were taken. Emperors employed entire bureaus of astronomers, their promotions tied to the accuracy of their predictions. Observatory towers, like the one still standing in Dengfeng, weren't just scientific instruments, they were early warning systems for the state. By the time Jesuit missionaries brought European astronomy to China in the 17th century, they found a system so refined that their own telescopic discoveries were cross-checked against millennia-old records. Yet for all their sophistication, Chinese astronomers never separated the practical from the prophetic. A supernova wasn't just a dying star, it was a dialogue between heaven and earth. The stars didn't merely shine, they governed. In this worldview, the universe wasn't a cold, mechanical place, but a living entity, its rhythms as intimate as the turning of seasons in a peasant's field. That's the true legacy of these star maps, not just as scientific documents, but as bridges between the human and the cosmic, where every flicker in the night sky was a character in an unending celestial drama. Vedic astronomers didn't just observe the stars, they envisioned the cosmos as a breathing entity, pulsing through cycles of creation and dissolution, so vast they make modern geologic time seem fleeting. In the Rig Veda, one of humanity's oldest texts, there's a hymn that describes the sun's path as a golden wheel with 12 spokes, mirroring the zodiac divisions Western astronomy wouldn't formalize for millennia. But what's truly staggering is their grasp of the precession of equinoxes, the slow wobble of Earth's axis that shifts the position of stars over 26,000 years. While Hipparchus is often credited with discovering this phenomenon in the 2nd century BCE, the Vedas allude to it as early as 1500 BC, calling it the Great Year, where constellations gradually trade places in the dawn sky. How did they detect such a subtle shift without telescopes? The answer lies in centuries of priest astronomers tracking solstice sunrises against temple alignments, their observations refined into a cosmic clockwork. The Surya Siddhanta, a Sanskrit text dating back at least to the 4th century CE, reads like an ancient astrophysics manual. Its calculations for planetary diameters and distances, though not perfectly accurate by modern standards, reveal a mathematical sophistication that rivals Ptolemy's work. It describes Earth as a sphere long before European scholars accepted the idea, and calculates its circumference with an error margin of less than 1%. Eclipses weren't mystical omens here, but predictable events, forecast using algorithms that accounted for the moon's elliptical orbit. One passage even corrects for atmospheric refraction, noting how starlight bends near the horizon, a phenomenon Western science wouldn't quantify until the 17th century. These weren't lucky guesses, they were the fruits of a culture that treated astronomy as sacred geometry, where numbers bridged the human and divine. Time in this worldview wasn't linear but fractal. The Puranas speak of 4 ages yugas cycling like seasons, with universes inhaling and exhaling over spans of billions of years. A single day of Brahma, they claimed, lasts 4.32 billion earthly years, eerily close to modern estimates of Earth's age. At observatories like Jaipur's Jantar Mantar, massive stone instruments tracked these cycles with uncanny precision. The Samrat Yantra, a sundial towering over 90 feet, could tell time down to 2 seconds, a feat of engineering that left British colonial astronomers stunned. What set Vedic astronomy apart was its refusal to separate science from spirituality. Temples like Konark's Sun Temple doubled as astronomical tools, their carvings encoding solstice alignments while depicting the sun god Surya riding his chariot across the sky. The nakshatras, their lunar zodiac, weren't just star clusters but cosmic deities, each governing human fate as precisely as they marked celestial longitude. When Aryabhata proposed in the 5th century that Earth spins on its axis, he didn't present it as a radical theory, but as part of a rhythmic dance described in sacred texts. This holistic vision challenges our modern divide between empirical and mystical. The same scholars who calculated pi to 4 decimal places also composed hymns to the planets as living beings. Their legacy whispers a provocative idea that the universe isn't just equations and inert matter, but a living, breathing entity, one ancient India mapped not just with mathematics but with poetry and reverence. In an age where we've traded star myths for satellite data, their work reminds us that the night sky was never just a puzzle to solve, but a story to be lived. Across the vast Pacific, where the horizon stretches endlessly in every direction, the Polynesian wayfinders performed feats of navigation that still defy modern understanding. Without compasses, without maps, without even a written language to record their knowledge, they crossed thousands of miles of open ocean, not by chance but by design. Their secret, a celestial roadmap etched not in ink or stone, but in memory, passed down through chants, stories, and generations of careful observation. They didn't just sail, they danced with the stars, the waves, even the flight patterns of birds, turning the natural world into a living navigation system. At the heart of their mastery lay the stars not as distant points of light, but as ancestors and guides. Constellations like the Pleiades, known to them as Matariki, weren't just pretty clusters, they were signposts. When Matariki rose just before dawn, it signaled the start of the planting season. When it disappeared below the horizon, it marked the time for long voyages. But the stars alone weren't enough. The wayfinders memorized the exact spot where each one would rise and set along the horizon, creating a mental compass that shifted with the seasons. A star rising directly east in June might inch northward by December, and they knew every subtle movement like the back of their hand, yet the sky was only part of the story. The ocean itself spoke to them. They learned to read the swells, the way waves reflected off distant islands, creating patterns invisible to untrained eyes. A faint change in the rhythm of the waves might hint at land over the horizon long before it came into view. Even the color of the water held clues. Deeper blues signaled open ocean, while lighter shades whispered of shallows or lagoons nearby. And then there were the birds. The flight paths of terns and frigatebirds became living arrows pointing the way to land. Some species would fly out to sea at dawn to fish and return at dusk. Follow them home and you'd find an island. What's truly humbling is how they preserved this knowledge. Without writing, every detail had to be memorized through oral traditions, complex chants that encoded star paths, wave behaviors, and seasonal winds. Apprentices spent years learning these chants, often starting in childhood, their teachers testing them relentlessly. A single mistake in recitation could mean missing an island and sailing into oblivion. This wasn't just navigation. It was an unbroken chain of wisdom stretching back centuries, where every generation added their own observations, refining the knowledge like a living, breathing map. So how did they achieve such precision? By treating the entire Pacific as their classroom. They didn't rely on instruments because they didn't need them. Their instruments were the world around them, the feel of the wind on their cheeks, the taste of salt in the air, the way the stars trembled just slightly differently when land was near. Modern navigators using GPS might scoff at these methods until they realized that Polynesian voyagers could detect islands they couldn't yet see, simply by reading the subtle language of nature. Perhaps the greatest testament to their skill came in the 1970s when the Hokulea, a reconstructed Polynesian voyaging canoe, sailed from Hawaii to Tahiti using only traditional methods, no compass, no charts, just the ancient knowledge revived. Against all odds, they arrived with pinpoint accuracy, proving that these techniques weren't just folklore. They were science honed over millennia, and that's the real wonder here. In a world obsessed with technology, the Polynesians remind us that the most advanced tool is still the human mind, trained, attentive, and deeply connected to the rhythms of the earth and sky. Their legacy isn't just about how to navigate. It's about how to see the world as a living, breathing guide, if only we're willing to listen. Buried beneath the Mediterranean waves for 2,000 years, the Antikythera Mechanism wasn't just a relic, it was a revolution. When divers first pulled its corroded fragments from that shipwreck in 1901, they assumed it was just another piece of ancient pottery. But as the encrusted layers slowly revealed interlocking bronze gears, the world realized this was something extraordinary. Here was a device so advanced it could predict lunar eclipses decades in advance, track the 4-year cycles of the Olympic Games, and even model the irregular motions of the moon with a precision that wouldn't be matched again until the Renaissance. This wasn't just a tool, it was a miniature cosmos engineered in bronze. What makes the mechanism truly astonishing is its complexity. Modern X-ray scans have uncovered at least 30 intermeshing gears, some with teeth cut at precise angles to account for celestial irregularities. One gear even mimicked the moon's elliptical orbit using a pin and slot mechanism, an ancient analog for the mathematical concept of epicycles. The front dial displayed the Greek zodiac and Egyptian calendar, while tiny inscriptions acted as a user manual, explaining which celestial events would occur on any given date. Imagine holding a device no larger than a shoebox that could tell you not just the phase of the moon, but the exact hour an eclipse would darken the sky over Corinth or Alexandria. But here's the haunting question: was this mechanism unique, or was it just one survivor of a lost tradition of ancient technology? Cicero once wrote of a similar device built by Archimedes, which reproduced the motions of the sun, moon, and 5 planets. Could the Antikythera mechanism be a descendant of that earlier invention? The shipwreck dates to around 60 BCE, but the device's design suggests it might have been made decades earlier. If so, its existence hints at a Hellenistic world buzzing with mechanical innovation, a world where astronomy wasn't just observed but engineered. Theories abound about its origin. Some scholars point to Rhodes, home of the astronomer Hipparchus, whose theories on lunar motion align eerily with the mechanism's calculations. Others suggest Corinth or Syracuse, where Archimedes' legacy of intricate machines might have inspired its creation. Wherever it was built, its purpose was clear: to bridge the gap between human understanding and celestial mystery. The dials didn't just show time, they revealed the divine order, turning cosmic patterns into something you could hold in your hands. Yet the most poignant detail isn't its gears or predictions, it's what its discovery implies about lost knowledge. For centuries, historians assumed the ancient world lacked mechanical sophistication. The Antikythera Mechanism shatters that assumption. If something this advanced existed, what else might have been lost to time? Were there other devices, other marvels, swallowed by fires, wars, or the relentless sea? The mechanism is more than a scientific artifact. It's a whisper from the past, reminding us that history's pages are full of gaps, and that the ancients might have been far closer to the stars than we ever imagined. To the Babylonians, a lunar eclipse wasn't just an astronomical event. It was a scream in the night sky, a warning that the gods were angry. Their astronomers, who could predict these eclipses with uncanny accuracy, weren't just scientists, they were intermediaries between heaven and earth. When the moon darkened, the king would step down from his throne, replaced by a substitute who would bear the brunt of the god's wrath. After the eclipse passed, the stand-in ruler, often a convicted criminal, would quietly disappear, having fulfilled his grim duty. This wasn't mere superstition. It was a meticulously choreographed ritual, blending hard-won astronomical knowledge with deep-seated belief. The same scholars who calculated planetary orbits also penned omens like, "If Jupiter is dimmed, the king of Akkad will die," treating celestial movements as a cosmic telegraph system. Half a world away, Chinese imperial astronomers faced even higher stakes. Their observatories weren't just research centers, they were early warning systems for the state. A comet streaking across the sky might signal rebellion, a supernova the death of an emperor. The records from the Han Dynasty tell of astronomers executed for failing to predict eclipses, their heads rolling because they missed a celestial deadline. Yet these same court astrologers also made breakthroughs we'd recognize as science today. They tracked sunspot cycles centuries before Galileo, documented supernovas so precisely that modern astronomers can still locate their remnants, and maintained star catalogs rivaling those of the Greeks. For them, the line between divination and astronomy didn't exist. Reading the stars was like reading the emperor's mail, a sacred duty with life or death consequences. This fusion of observation and interpretation wasn't limited to ancient empires. The Maya saw Venus not just as a planet but as a god, Kukulkan, whose appearances dictated the timing of wars. Their Dresden Codex contains tables predicting Venus's movements with astonishing precision. Yet these calculations weren't just for farming or navigation. They determined when to launch military campaigns, believing battles fought under Venus's morning star phase would bring victory. Even the Hopewell culture of North America built enormous earthworks aligned to lunar standstills, where ceremonies coincided with celestial events, weaving astronomy into the fabric of spiritual life. What's fascinating is how these ancient practices echo today, often in ways we don't fully recognize. The word disaster comes from the Latin disastra, literally bad star. When people check horoscopes or blame full moons for strange behavior, they're tapping into a tradition as old as civilization itself. Modern eclipse chasers may not fear celestial omens. but the awe they feel standing in the moon's shadow isn't so different from what Babylonian priests experienced millennia ago. The stars haven't changed, only how we explain them. Perhaps that's the real lesson here. Ancient cultures remind us that astronomy was never just about charting the heavens. It was about finding our place in them, interpreting the universe's whispers as guidance, warning, or comfort. In an age of satellites and space telescopes, we've traded omens for equations, but the fundamental human impulse remains the same: to look up and wonder what it all means. The stars, it seems, have always been more than balls of gas. They've been mirrors reflecting our deepest fears, hopes, and questions back at us. The flames that consumed the Library of Alexandria didn't just burn parchment and papyrus, they erased entire worlds of thought. Imagine walking its halls in the 3rd century BCE, where scrolls from Babylon, Greece, Egypt, and beyond stretched as far as the eye could see. Among them were astronomical treatises so advanced they might have rewritten history. The library wasn't just a building. It was the beating heart of ancient scholarship, a place where Eratosthenes calculated Earth's circumference with astonishing accuracy, where Hipparchus compiled star catalogues so precise they rival modern datasets. Yet all that remains of their work are fragments, second-hand quotes, and the haunting question: what cosmic insights turned to ash that day? One tantalizing clue lies in the writings of Seneca, who referenced lost texts describing planetary motions with loops and retrograde paths, a clear nod to the elliptical orbits we now associate with Kepler's laws. Could the ancients have grasped these concepts millennia earlier? The Antikythera Mechanism suggests they might have. Its intricate gears, capable of modeling the moon's irregular orbit, hint at a sophistication we've only begun to uncover. Even more intriguing are the scattered references to Aristarchus of Samos, who proposed a heliocentric solar system in the 3rd century BCE, 1800 years before Copernicus. His original work vanished, surviving only in a passing mention by Archimedes. How many other revolutionary ideas shared the same fate? But Alexandria wasn't alone in its tragedy. The House of Wisdom in Baghdad, another beacon of knowledge, fell to the Mongols in 1258. Witnesses described the Tigris River running black with ink from discarded manuscripts, among them Arabic translations of Ptolemy's lost works and Persian star charts detailing unknown supernovae. In Mesoamerica, Spanish conquistadors burned Mayan codices by the thousands, erasing astronomical records that might have explained their uncanny eclipse predictions. Even China's imperial libraries, though vast, were ravaged by wars and censorship, leaving gaps in their otherwise meticulous celestial chronicles. What makes these losses so devastating is the randomness of what survived. A single waterlogged manuscript, a quote in a marginal note, a carving on a temple wall, these fragile threads are all that connect us to ideas that once shaped civilizations. The irony is crushing. Cultures that mapped stars with pinpoint accuracy couldn't safeguard their own knowledge from fire, war, or time. Yet there's hope in the fragments. When archaeologists deciphered the charred remains of a Roman villa's library near Herculaneum, they found previously unknown texts by Epicurus, their letters visible only through advanced X-ray imaging. Similarly, multispectral scanning has resurrected erased palimpsests, medieval manuscripts where monks scraped away older astronomical texts to reuse the parchment. Beneath the surface, ghostly traces of star coordinates and planetary tables still linger, waiting to be read. These scattered survivors remind us that history isn't a straight line but a puzzle with half the pieces missing. Every recovered fragment, whether it's a Babylonian clay tablet or a Tibetan cave manuscript, is a whisper from the past, challenging our assumptions about ancient knowledge. The real tragedy of Alexandria isn't just what was lost, but how it warps our perception of antiquity, making us underestimate the brilliance of those who came before. Their legacy isn't gone, it's buried, waiting for the next patient scholar to piece it back together. Standing in the passage tomb of Newgrange on the winter solstice is like stepping into a 5,000-year-old time machine. As dawn breaks, a narrow beam of sunlight creeps through the roof box, a precisely aligned opening above the entrance, and slowly floods the inner chamber with golden light. This isn't an accident, it's a meticulously engineered phenomenon, a celestial handshake between stone and sun that repeats like clockwork every December. The builders of Newgrange didn't just stack rocks, they encoded the rhythm of the seasons into their architecture, turning a burial mound into a solar observatory. And they weren't alone. Across the globe, from the deserts of the American Southwest to the plains of Egypt, ancient cultures wove astronomy into their landscapes in ways we're only beginning to decipher. Take Choco Canyon, where the ancestral Puebloans carved spiral petroglyphs high on Fajoda Butte. At noon during the summer solstice, a dagger of sunlight slices through the rock formations to bisect the largest spiral, an event so precise it could only result from generations of patient observation. Nearby, the Great North Road stretches straight as an arrow for 30 miles, aligning with the moon's northernmost rise during its 18.6-year cycle. These aren't just artistic flourishes, they're proof of a culture that tracked lunar standstills with the same dedication modern astronomers reserve for black holes. What's revolutionary about archaeoastronomy is how it forces us to rethink the capabilities of so-called primitive societies. The Maya didn't need telescopes to map Venus's 8-year cycle. They used nothing but sticks and shadows. The builders of Stonehenge didn't have calculators, yet they positioned the heel stone to mark the summer solstice sunrise within a margin of error smaller than a pinky finger. Even the Great Pyramid's descending passage targets the pole star of its era, Thuban, with an accuracy that defies coincidence. These feats weren't mystical, they were mathematical, the product of minds every bit as sharp as Newton's or Einstein's. But here's the twist, not all alignments are what they seem. Some astronomical connections proposed by early researchers turned out to be wishful thinking, like the way random scratches on a rock might resemble a constellation if you squint hard enough. Modern archaeoastronomers use statistical analysis to separate celestial intent from coincidence, measuring alignment probabilities down to fractions of a degree. When a site like Machu Picchu's Intihuatana stone casts no shadow at solar noon during equinoxes, or when Cambodia's Angkor Wat's western gate frames the spring equinox sun, the numbers don't lie. These are deliberate designs, frozen echoes of cultures that saw the sky as both calendar and compass. The real magic lies in the diversity of these cosmic blueprints. In Ohio's Hopewell earthworks, geometric enclosures mirror lunar eclipse cycles, while Peru's Nazca lines may have functioned as giant horizon markers for tracking star risings. Even England's lesser-known Callanish stones form a cross-shaped observatory where the moon skims the horizon like a silver ball during its major standstill. Each culture spoke the same celestial language but wrote it in different dialects, some with monoliths, others with paint or pottery. What unites them all is a profound truth. Astronomy wasn't a niche science for the ancients. It was the backbone of agriculture, religion, even politics. When a Babylonian king needed legitimacy, he pointed to celestial omens. When Egyptian priests set temple foundations, they waited for Sirius to rise. These weren't just stargazers, they were cosmic architects, building civilizations under the watchful eye of the heavens. And with every alignment we decode, we're not just uncovering lost knowledge, we're relearning how to see the sky as they did, not as a void to conquer, but as a living map etched in light. The Dogon people of Mali tell a story that sends shivers down the spines of astronomers, a story about Sirius, the brightest star in our night sky. According to their oral traditions, passed down through generations, Sirius has a tiny, invisible companion star, one so dense that a handful of its matter would weigh as much as a grown man. What's astonishing is that this companion, Sirius B, wasn't confirmed by telescopes until the 19th century. The Dogon called it Po-Tolo, a star made of a mysterious, impossibly heavy metal, and described its 50-year elliptical orbit around Sirius with eerie accuracy. How could a remote African tribe without telescopes or written records know about a star invisible to the naked eye? One theory points to ancient contact with advanced civilizations. The Dogon claim their knowledge came from amphibious beings called the Nommo, who descended from the Sirius system in a great ark. These visitors, described as fish-like creatures, allegedly shared celestial secrets with the tribe's ancestors. Skeptics dismiss this as myth, but others wonder if it echoes real encounters with a forgotten culture, perhaps even the Egyptians, who revered Sirius as the star of Isis and aligned their temples to its heliacal rising. The Egyptians, after all, recorded celestial events with precision, and their knowledge could have traveled along trade routes stretching deep into Africa. Then there's the counter-argument, contamination. In the 1930s, French anthropologists Marcel Grioul and Germain Dieterlen lived with the Dogon and documented their star lore. Critics suggest the researchers, steeped in Western astronomy, might have unintentionally influenced the tribe's narratives or overinterpreted their symbolism. After all, Sirius B had been discovered decades earlier, and the idea of an invisible companion wasn't unheard of in popular science. Could fragments of modern knowledge have woven themselves into ancient oral traditions, creating a tantalizing but false mystery? The debate takes a sharper turn when examining the Dogon's other astronomical claims. They describe a third star in the Sirius system, something astronomers still haven't found, though some theories suggest it might exist. They also speak of Saturn's rings and Jupiter's 4 largest moons, celestial details impossible to see without lenses. Yet these claims are murkier, less consistent than the Sirius B lore, leaving room for doubt. What's undeniable is how the Dogon mystery forces us to confront the fragility of history. If their knowledge is genuinely ancient, it hints at a lost thread of astronomical wisdom, preserved against all odds. If it's a modern hybrid of myth and borrowed facts, it reveals how easily we project our desires onto the past, yearning for proof that ancient cultures were wiser than we thought. Either way, the story of Po-Tolo isn't just about stars, it's about who gets to write the narrative of discovery, and how easily the lines between observation, tradition, and imagination can blur. Long before star charts and planetarium apps, ancient cultures wrapped their celestial knowledge in stories so vivid they could be told around campfires for generations. Take the Greek myth of Phaethon, the reckless son of the sun god Helios, who lost control of his father's chariot and scorched the earth. On the surface, it's a cautionary tale about hubris, but look deeper and you'll find something astonishing. The path Phaethon allegedly took across the sky mirrors the ecliptic, the sun's annual journey through the zodiac. His wild ride, a poetic description of solar activity so intense it might reference a real geomagnetic storm, one that left traces in ancient tree rings and ice cores. The Greeks weren't just spinning fables, they were encoding celestial mechanics in narrative form. Half a world away, Aboriginal Australians mapped the cosmos through the emu in the sky, a constellation not of stars but of the dark patches between them. The emu's shape, formed by the dust lanes of the Milky Way, changes position with the seasons, its posture signaling when to gather eggs or when rivers would flood. These stories weren't entertainment, they were survival manuals, blending astronomy with ecology in a way modern science is only beginning to appreciate. When an elder points to the emu's stretched neck in the spring sky, they're not just sharing folklore, they're reading a celestial calendar etched in galactic dust. Even the Norse had their own cosmic code. The tale of the wolf's girl chasing the sun wasn't just a dramatic explanation for solar eclipses, it preserved precise observations. Viking sagas describe the sun swallowing the moon during eclipses, a detail that reveals naked eye recognition of the moon's shadow mechanics. Their stories pinned abstract concepts to memorable characters. Thor's hammer strikes were thunderstorms. The Rainbow Bridge Bifrost was the aurora borealis, turning the sky into a theater where science and myth shared the stage. What's striking is how universal this practice was. The Maya depicted Venus as the war god Kukulkan, his movements dictating battle dates. The Cherokee wove the Pleiades into a story about 7 boys who danced into the sky, a mnemonic for the cluster's rising and setting. These narratives did more than entertain. They transformed the night sky into a classroom where complex ideas could be passed down without a single written word. But here's the twist. These myths often contained layers of meaning. The Babylonian epic of Gilgamesh includes a flood story that mirrors climatic records of ancient deluges, while its descriptions of the Bull of Heaven may reference the constellation Taurus. The line between legend and empirical observation was porous. When Polynesian navigators spoke of Maui slowing the sun, they weren't just explaining daylight, they were encoding knowledge of the solstices, when the sun appears to pause in its seasonal journey. This fusion of storytelling and science challenges our modern divide between fact and fiction. For ancient cultures, myths weren't lies, they were frameworks, compressing generations of observation into narratives sticky enough to survive centuries. In an age before textbooks, the best way to remember that Orion's belt points to Sirius wasn't to jot down coordinates. It was to tell a story about a hunter and his loyal dog, forever chasing each other across the sky. The real magic lies in realizing how much hard science was hidden in plain sight, disguised as bedtime stories under the stars. When Babylonian scribes pressed their styluses into wet clay to record a lunar eclipse in 323 BC, they weren't just documenting a celestial event, they were unknowingly creating a timestamp for future scientists. That same eclipse, described as the moon was eclipsed in the middle watch, now serves as a critical data point for astronomers calculating how Earth's rotation has slowed over millennia. The tiny discrepancies between ancient eclipse timings and modern predictions reveal something extraordinary. Our planet's spin isn't constant. Tidal friction from the moon's gravity acts like a cosmic break, stretching each day by about 1.7 milliseconds per century. Without these clay tablet time capsules, we might never have detected such subtle changes. Chinese court astronomers took eclipse records even further, treating them as imperial emergencies. The Bamboo Annals, chronicling events from 1600 BC onward, describe eclipses with military precision. The sun was eaten at dawn, stars appeared. One entry from 1300 BC notes a total eclipse lasting from the left side, matching modern retrocalculations to within minutes. These weren't passive observations, they were statecraft. Emperors interpreted eclipses as celestial report cards, with inaccurate predictions sometimes costing astronomers their heads. That pressure bred astonishing accuracy. By the Tang dynasty, their eclipse forecasts were reliable to within 15 minutes, all without telescopes or clocks. Arab scholars later refined these techniques to near perfection. In 890 CE, the astronomer Al-Batani used eclipse records from Babylon and Alexandria to recalculate the length of the solar year, coming within 2 minutes of today's value. His work, preserved in medieval manuscripts, also revealed another puzzle. The moon's orbit is gradually expanding, pushing it about 3.8 centimeters farther from Earth each year. That tiny drift, detectable only by comparing ancient and modern eclipse durations, explains why totality won't last forever. In 600 million years, the moon will appear too small to fully cover the sun. What's truly humbling is how these records transcend their original purpose. Babylonian eclipse omens, meant to warn kings of impending doom, now help NASA engineers fine-tune spacecraft trajectories. Chinese astrologers, fearing heavenly wrath, inadvertently created a dataset for studying Earth's core, since fluctuations in rotation speed hint at molten iron swirling beneath our feet. Even the Maya's Dresden Codex, with its eclipse warning glyphs, contributes to understanding solar activity cycles. These ancients weren't just staring at the sky, they were building a cosmic yardstick, one that stretches across centuries to measure changes invisible in a single lifetime. The most poetic twist, some eclipse records outlasted the civilizations that made them. When a 9th century BCE Assyrian tablet mentions darkness at noon, it does so in a doomed empire that would soon collapse. Yet that same darkness now illuminates our understanding of planetary motion, proving that while kingdoms fade, careful observation endures. Every time a modern astronomer adjusts their models based on a 2,000-year-old clay tablet, it's more than science, it's a conversation across time, where the past keeps teaching the present how to read the sky. Buried in the sands of time, the Egyptian merkhet looks deceptively simple, a palm-sized notched stick with a dangling plumb line. Yet this humble tool, used as early as 600 BC, was the ancient world's precision timekeeper. On clear nights, priests would align its central groove with Polaris, the North Star, while the plumb line marked true vertical. By tracking how stars crossed these sightlines, they could divide the night into hours with startling accuracy. These star clocks weren't just for rituals, they regulated the Nile's flood cycles, turning astronomy into agriculture's lifeline. The genius lies in their adaptability. The same device that timed temple ceremonies also helped architects orient pyramids to cardinal directions within a fraction of a degree. Meanwhile, high in the Andes, the Inca were solving similar problems with radically different tools. Quippus, intricate knotted cords that served as their astronomical database. While most associate Quippus with census records or tax rolls, recent studies reveal some encoded celestial patterns. Certain knot sequences match the 18.6-year lunar cycle, while color variations may represent planetary movements. Without written language, the Inca transformed fiber into a three-dimensional spreadsheet, where each knot's position, size, and hue held meaning. Spanish chroniclers noted how Quipu specialists could read eclipse predictions from these cords, suggesting a tactile astronomy as sophisticated as it was portable. Halfway across the world, the Nebra sky disk, a 3,600-year-old bronze artifact found in Germany, blurs the line between tool and artwork. Its gold inlays depict the Pleiades cluster, a crescent moon, and what may be a solar barge surrounded by horizon arcs. Some scholars believe it functioned as a primitive calendar, with the Pleiades position marking planting seasons. Others argue it was a ceremonial object, its celestial motifs mapping the afterlife. What's undeniable is its precision. The angles between the arcs match solstice sunrises at the Mittelberg Hill where it was buried, proving its creators tracked the sun's yearly dance with naked eye accuracy. Then there's the Javanese kraton, a lattice-like instrument used by Southeast Asian navigators. Made of bamboo rods and calibrated to local latitudes, It allowed sailors to measure star altitudes by aligning specific notches with the horizon. Unlike Western astrolabes, the Kraken was lightweight and waterproof, perfect for monsoon season voyages. Its design reveals a deep understanding of celestial navigation tailored to the tropics, where different stars dominate the sky. What unites these artifacts is their elegant practicality. Whether it's a Chinese armillary sphere's nested rings modeling planetary orbits or a Polynesian star compass carved into driftwood, each culture developed tools that turned local skies into measurable data. Their diversity is a testament to human ingenuity. No telescopes, no problem. From knotted strings to bronze discs, necessity didn't just birth invention, it sculpted masterpieces. The Babylonians didn't just map the stars, they sliced the sky into 12 equal portions like a cosmic pie chart, and in doing so, laid the foundation for the zodiac we recognize today. Around the 5th century BCE, their astronomers divided the ecliptic, the sun's apparent path across the sky, into 12 30-degree segments, each named after the constellation that once occupied it. This wasn't astrology as we think of it now. It was a practical system for tracking time and predicting seasonal shifts. The spring equinox, for example, fell in the constellation they called Emuel. A pin, the plough, marking the start of the agricultural year. Their zodiac was less about personality traits and more about survival, a celestial almanac etched in clay. When the Greeks encountered Babylonian astronomy, they didn't just adopt it, they reinvented it. By the 3rd century BCE, Greek scholars had merged the Babylonian framework with their own rich mythology. The plough became Aries, the ram of the golden fleece, while the great twins transformed into Gemini, immortalizing Castor and Pollux. Ptolemy, writing in his Tetrabiblos, took it further, assigning planetary influences to each sign and weaving fate into the stars. What had been a farmer's calendar now became a mirror of human destiny, where the position of Mars or Venus at birth could shape a person's character. The Greeks didn't just borrow the zodiac, they gave it a soul, but the story doesn't stop there. Indian astronomers, encountering Greek astrology via trade routes, adapted it to their own cosmic vision. In Vedic astrology, or Jyotisha, the 12 signs remained, but the interpretations shifted. Aries wasn't just a ram, it was Mesha, a fiery symbol of leadership tied to the god Agni. The Indians also introduced the concept of lunar mansions, or nakshatras, adding another layer of nuance. Meanwhile, Arab scholars like al-Biruni preserved and refined the system during Europe's Dark Ages, ensuring its survival. Their star catalogues, written in Arabic, became the bridge between ancient and Renaissance astronomy. What's fascinating is how fluid the zodiac proved to be. The Babylonians never intended their constellations to dictate love lives or career choices, yet over centuries, cultures projected their own stories onto the same 12 slices of sky. Even the constellations themselves drifted due to precession. Ptolemy's Aries now aligns with Pisces, a shift that would have baffled ancient stargazers. Modern horoscopes, with their daily predictions, are a far cry from the original celestial timekeepers, but they're part of the same unbroken chain. The zodiac's journey from Babylonian clay tablets to smartphone apps is a testament to humanity's endless desire to find meaning in the stars, no matter the era or culture. Deep in the caves of Lascaux, where torchlight flickered against walls untouched by sunlight for 17,000 years, ancient artists painted more than just animals. Hidden among the bulls and horses are clusters of dots that mirror the Pleiades star group, their arrangement too precise to be accidental. This wasn't mere decoration, it was humanity's first star map, a prehistoric planetarium etched in ochre and charcoal. But the real revelation lies in what these markings imply. Long before cities or writing, people were tracking celestial patterns with the same intensity as modern astronomers. The same cosmic curiosity appears in the standing stones of Scotland's Callanish, where Neolithic builders aligned monoliths to the moon's most extreme risings and settings. Every 18.6 years, when the moon enters its major standstill, it appears to skim the horizon directly between these stones, an event so rare it would have required generations of observation to pinpoint. Across Europe, similar lunar calendars carved into bone or stone, like the 30,000-year-old Blanchard plaque, tally moon phases in sequences that match modern counts. These weren't crude tallies, they were mathematical records, proof that Ice Age hunters could predict celestial events with the precision of an almanac. What's most striking is how these ancient skywatchers encoded their knowledge. In Turkey's Göbekli Tepe, the world's oldest known temple, pillars engraved with scorpions and vultures may represent constellations visible 11,000 years ago. A carving of a fox carrying a round object could depict a comet or meteor, its tail mirroring the streaming debris of a celestial visitor. Even the famous Star Boy burial in Germany, a child interred with mammoth ivory beads arranged in constellations, suggests that the night sky wasn't just observed but ritualized, woven into the very fabric of spiritual life. The common thread, these cultures separated by millennia and continents all shared one insight: the heavens were a story waiting to be read. Whether it was Aboriginal Australians tracking the emu-shaped dust lanes of the Milky Way or Native American tribes building medicine wheels aligned to solstice sunrises, they recognized that the sky wasn't random. It pulsed with rhythms that governed seasons, migrations, and survival. Their primitive star charts, far from being superstition, were the bedrock of science, born from countless nights of patient observation. Perhaps the most humbling realization is how much they saw without telescopes or writing. The Lascaux artists didn't need software to identify the Pleiades. Their eyes, attuned to darkness we can scarcely imagine, picked out patterns we now require apps to find. Their legacy isn't just in the paint or stone they left behind. It's in the unbroken lineage of wonder that connects their firelit vigils to our space telescopes, proving that the urge to map the unknown is written in our bones as surely as the stars are written across the night. While Europe stumbled through the Dark Ages, the Islamic world was experiencing an astronomical renaissance that would change the course of science. In 9th century Baghdad, the House of Wisdom wasn't just a library. It was a buzzing hive of intellectual activity where scholars translated Greek, Persian, and Indian texts while making groundbreaking discoveries of their own. Among them stood al-Battani, whose meticulous observations corrected Ptolemy's planetary models and calculated the solar year to within minutes of its true length. His star catalogue, the Zij al-Sabai, became the gold standard for astronomers across 3 continents, proving that the geocentric model had flaws even before Copernicus was born. But the real marvels emerged from the great observatories of the Islamic world. Take the Maraghe Observatory in 13th century Persia, where Nasir al-Din al-Tusi designed instruments so precise they could track Mercury's elusive orbit. His Tusi couple, a geometric device that resolved inconsistencies in Ptolemy's system, later inspired Copernicus himself. Historians have found near-identical diagrams in the Polish astronomer's notes. Then there's Ulugh Beg's observatory in Samarkand, where a gargantuan sextant carved into the Earth measured star positions with unprecedented accuracy. His star catalogue, compiled in the 1420s, pinpointed over 1,000 stars with an error margin smaller than the width of a full moon. What set these scholars apart wasn't just their tools, it was their mindset. While medieval Europe debated whether astronomy conflicted with scripture, Islamic scientists like Ibn al-Haytham wrote treatises on the scientific method, insisting that theories must align with observable reality. Andalusia's Al-Zarqali invented the universal astrolabe, adjustable for any latitude, while Ibn Yunus documented eclipses and planetary conjunctions so accurately that modern astronomers still reference his work to study Earth's rotation. Their breakthroughs weren't accidents, they were the fruits of a culture that prized measurement, peer review, and relentless curiosity. The most enduring legacy of this golden age, though, may be its role as a bridge between eras. When the Mongols sacked Baghdad in 1258, scholars fleeing the chaos carried precious manuscripts to places like Toledo, where Christian, Jewish, and Muslim translators worked side by side to preserve them. Ptolemy's Almagest, nearly lost to Europe, survived because of Arabic translations. The trigonometry developed by al-Battani and al-Khwarizmi became the backbone of Renaissance astronomy. Even the words we use today, algebra, azimuth, zenith, are Arabic in origin, silent reminders of an era when the stars spoke in the language of the Quran. This wasn't just preservation, it was transformation. Islamic astronomers didn't parrot Greek knowledge, they tested it, refined it, and sometimes dismantled it. When Copernicus proposed his heliocentric model, he stood on the shoulders of giants who had spent centuries questioning Ptolemy's errors. The real revolution began not in 16th century Poland, but in the marble-floored observatories of Persia, the paper-filled scriptoriums of Cordoba, and the bustling streets of medieval Damascus, where the night sky wasn't feared, it was studied, admired, and ultimately understood. In the quiet scriptoriums of medieval monasteries, where monks bent over parchment by candlelight, astronomy survived not despite Christianity, but because of it. While Europe's secular libraries crumbled, these cloistered scholars preserved Ptolemy's star charts alongside Psalter's, seeing no contradiction between faith and the study of celestial mechanics. To them, the heavens weren't just physical phenomena, they were the work of his fingers, as Psalm 19 declared. Hildegard of Bingen, the visionary abbess of the 12th century, wove astronomy into her mystical writings, describing the planets as living sparks orbiting in divine harmony. Her cosmic visions, though steeped in theology, contained startlingly accurate details like her description of the moon's reflected light, which contradicted the common belief that it emitted its own glow. The monastic approach to science was deeply practical. Benedictine abbeys like Cluny and Monte Cassino became centers for timekeeping, where monks calculated Easter's date using complex lunar cycles, a task requiring precise astronomical knowledge. Their computus manuals, filled with planetary tables and eclipse predictions, were among the era's most sophisticated scientific texts. Even the architecture of their churches served a dual purpose. Certain abbey windows aligned with solstice sunrises, transforming sacred spaces into solar observatories where light and liturgy intertwined. Yet tensions simmered beneath this synthesis. When Gerbert of Aurillac, the future Pope Sylvester II, introduced Arabic numerals and astrolabes to Europe in the 10th century, some clerics accused him of dabbling in dark arts. The Church's embrace of Ptolemy's geocentric model, which placed Earth at the universe's center, later hardened into dogma, stifling challenges to the cosmic order. But even within these constraints, monks like Richard of Wallingford made breakthroughs. His 14th century clock at St. Albans Abbey didn't just mark hours, it modeled planetary motions, a mechanical cosmos ticking away above the choir stalls. What's often overlooked is how these medieval scholars laid groundwork for the scientific revolution. The Venerable Bede's 8th century writings on tides revealed an understanding of the moon's gravitational pull centuries before Newton. Dominican friars like Albertus Magnus dissected Aristotle's physics while insisting nature must be studied empirically, not just through scripture. Their work, though framed in theological terms, nurtured a curiosity that would eventually outgrow its medieval shell. The real legacy of monastic astronomy lies in its stubborn refusal to let knowledge die. When Charlemagne mandated the teaching of astronomy in cathedral schools, he wasn't promoting heresy, he was ensuring farmers could read the stars to plant crops. The stars to these medieval minds were both signs and tools, messages from God and guides for human survival. In an age often dismissed as dark, they kept the light of inquiry burning, not as a rival to faith, but as its companion, proving that even in the shadow of cathedrals, science could find a way to shine. When Copernicus first dared to suggest that Earth revolved around the sun, he wasn't just defying centuries of dogma. He was resurrecting an idea older than Rome itself. 2,000 years before the Renaissance, Greek astronomer Aristarchus of Samos had already proposed a heliocentric universe, his work preserved only in a passing mention by Archimedes. Islamic scholars like al-Sijzi and al-Biruni had later refined these ideas, crafting elaborate models where Earth moved through space. Yet by Copernicus's time, these breakthroughs had faded into obscurity, buried under the weight of Ptolemy's Earth-centered cosmos. The real revolution wasn't just in the math or the observations. It was in the rediscovery of a truth that had been waiting patiently in forgotten manuscripts, like a seed preserved through winter. What's striking is how Copernicus framed his groundbreaking work. His book, On the Revolutions of the Heavenly Spheres, leaned heavily on the same geometric tools Ptolemy had used, almost as if he were whispering his heresy in the language of the establishment. He didn't present heliocentrism as a radical break, but as a return to purer, more elegant principles, ones that eliminated the clunky epicycles Ptolemy needed to explain planetary loops. This wasn't accidental. Copernicus knew his audience, theologians and scholars steeped in classical traditions. By grounding his model in Greek geometry and citing ancient authorities, he made the unthinkable seem inevitable, even respectable. But the story doesn't end with Copernicus. His work ignited a chain reaction that spanned generations. Tycho Brahe's precise observations, Kepler's elliptical orbits, Galileo's telescopic proofs, each built on foundations laid centuries earlier. Kepler, in particular, found inspiration in the mystic geometry of Pythagoras, who'd believed the universe moved to mathematical harmonies. Even Newton, whose laws of motion sealed heliocentrism's triumph, credited the ancients with glimpsing fragments of the truth. The so-called Copernican revolution wasn't a sudden upheaval. It was a slow reawakening, a dialogue across millennia where each generation added its voice to an argument as old as the stars themselves. The lesson here is humbling. Progress isn't always a straight line. Sometimes it's a spiral where ideas vanish only to resurface when the world is ready to hear them. The same sky that had whispered secrets to Aristarchus and al-Biruni finally found ears willing to listen in Renaissance Europe. And that's the real wonder of the Copernican moment. It reminds us that knowledge, even when suppressed or forgotten, never truly dies. It lingers in marginal notes, in half-remembered theories, waiting for the right minds to piece it back together. The universe, it seems, is patient. Its truths will always find their time. High in the Andes, where thin air makes the stars appear unnervingly close, the Inca engineered a solar observatory unlike any other. At Machu Picchu, the Intihuatana stone, often called the hitching post of the sun, casts no shadow during the equinoxes, its angles precisely calculated to mark the moments when day and night hang in perfect balance. But the real marvel lies beyond the famous citadel. On the outskirts of Cusco, 12 pillars known as the Sucanca once stood like silent sentinels on the horizon. As the June solstice approached, priests would watch from the fortress of Sacsayhuaman, noting where the sun rose between these stone markers to determine the exact date. This wasn't just ceremony, it was agricultural science. When the sun paused at the farthest pillar, it signaled the start of the planting season, turning astronomy into the foundation of empire. Meanwhile, in the arid cliffs of the American Southwest, the ancestral Puebloans were solving similar problems with radically different tools. At Choco Canyon, the massive kiva known as Cosa Rinconada features a window that perfectly frames the summer solstice sunrise, while petroglyphs on Fajoda but capture the moon's 18.6-year cycle with spiral carvings bisected by dagger-like sunlight. But what's truly astonishing is their lunar calendar etched into the rock face of Penasco Blanco, a series of small holes where shadows move like clock hands, tracking the moon's phases with pinpoint accuracy. These weren't passive observations, they were mathematical blueprints encoded in stone by people who saw the sky as both clock and compass. Further north, the Cahokia Mounds near modern-day St. Louis reveal another layer of celestial ingenuity. Woodhenge, a circle of towering red cedar posts, functioned as a massive solar calendar. On the equinoxes, the rising sun aligned with specific posts, while the winter solstice sunrise framed the Grand Monk's Mound in a blaze of light. Recent excavations suggest some mounds even mirrored star patterns, with their layouts mimicking the Pleiades or Orion's belt. For the Mississippian culture, these alignments weren't abstract, they dictated planting, harvest, and sacred ceremonies, binding earthly and cosmic rhythms into a single system. What unites these diverse traditions is their independence. The Inca had no contact with the Puebloans none with Cahokia, yet all arrived at strikingly similar solutions. The same curiosity that drove Babylonian scribes to track Venus also led Andean priests to measure solstices and ancestral Puebloan astronomers to chart lunar cycles. This wasn't coincidence, it was the inevitable result of humans confronting the same skies, the same need to predict seasons, the same awe at the cosmos's order. Their shared legacy proves something profound. Astronomy isn't a cultural invention but a universal language, written in sunlight on stone and whispered in the shadows of forgotten observatories. The real wonder lies in the details. At Wupatki in Arizona, a blowhole in the Earth's crust breathes with barometric pressure, its gusts timed to seasonal changes, a natural phenomenon the Puebloans link to celestial events. In Peru, the Nazca lines, often dismissed as mere art, include straight tracks aligned to solstice sunrises, suggesting they functioned as giant pilgrimage routes timed to astronomical events. Even the Inuit, far from these civilizations, developed their own sophisticated star lore, using the aurora to navigate and naming constellations like Quaterjuk, the celestial caribou. From desert to tundra, humanity's response to the night sky reveals not just intelligence, but a shared hunger to find meaning in the stars' silent dance. Along the banks of the Nile, where the river's annual floods painted the land black with fertile silt, the Nubians kept watch for Sirius. To them, the star's first appearance at dawn, known as the Heliacal Rising, was far more than a celestial event. It was nature's alarm clock, signaling the floodwaters that would nourish their crops. They called Sirius Sothis, weaving its movements into their agricultural calendar with a precision that rivaled Egypt's. But their astronomical prowess didn't stop there. Nubian stargazers also mapped the paths of Mercury and Venus, recording their cycles on temple walls and pottery shards. These weren't just decorative motifs, they were functional charts, guiding everything from planting seasons to religious festivals. Far to the west, beneath the vast Saharan sky, another intellectual revolution was unfolding in Timbuktu. By the 16th century, this desert crossroads had become a beacon of scholarship, where astronomers penned manuscripts so advanced they'd later influence European science. One such scholar, Ahmed Baba, compiled star catalogues that detailed planetary motions with mathematical rigor. His contemporaries used astrolabes crafted from brass and wood to measure star altitudes, while their treatises explored concepts like elliptical orbits centuries before Kepler formalized them. The Timbuktu astronomers didn't work in isolation. They drew on a network of knowledge stretching from Andalusia to Mali, proving that Africa's contributions to astronomy were anything but marginal. In Ethiopia, the rock-hewn churches of Lalibela tell a different but equally profound story. Their windows and doorways align with solstice sunrises, transforming sacred spaces into solar observatories. The Kebra Nagast, Ethiopia's ancient epic, describes celestial events with startling accuracy, including a reference to a red star that modern researchers suspect may document a supernova visible in the 14th century. Meanwhile, the Dogon people of Mali, as mentioned earlier, preserved oral traditions about Sirius B, a star invisible to the naked eye, with details that continue to puzzle astronomers today. What unites these traditions is their deep integration of astronomy into daily life. Unlike European observatories cloistered behind university walls, African celestial knowledge lived in the fields, the temples, and the marketplace. The great Zimbabwe ruins, with their tower aligned to the summer solstice, doubled as both political centers and astronomical tools. The San people of the Kalahari read the stars for navigation, using the Southern Cross to mark seasonal shifts. Even the Berbers of North Africa developed their own lunar calendar, etching star maps onto cave walls as teaching aids for desert travelers. The tragedy isn't that these achievements existed, it's how often they've been erased from history. Colonial narratives dismissed African astronomy as myth or superstition, ignoring the precision of Timbuktu's math or the Nubian star clocks. Yet the evidence survives in the alignment of monoliths at Namaratunga in Kenya, which mirror the constellations of 700 BCE, in the Benin bronzes depicting eclipse sequences, in the Swahili coast's navigational star charts that guided Indian Ocean trade. These aren't footnotes in the story of astronomy, they're whole chapters waiting to be read. Perhaps the most poignant lesson lies in how these traditions viewed the sky. For many African cultures, the stars weren't distant specks of light but ancestors, guides, and living entities. The Kung people of Botswana still tell of the Milky Way as the backbone of the night, a celestial axis holding up the heavens. This worldview, where science and spirituality intertwine, challenges the modern divide between empirical observation and cosmic wonder. It reminds us that mapping the stars was never just about calculation. It was about connection, a dialogue between humanity and the infinite. To the Aboriginal peoples of Australia, the night sky isn't just a scattering of stars, it's a living storybook, written in the dark spaces between the light. Where Western astronomy traces constellations by connecting bright dots, indigenous skywatchers saw shapes in the cosmic shadows, like the emu in the sky, its sprawling form outlined by the dust lanes of the Milky Way. This celestial emu isn't static, its posture shifts with the seasons. When it appears stretched high in the April sky, legs dangling toward the horizon, it signals the time to gather emu eggs. By August, as it descends horizontally, it warns that the eggs have hatched and hunting season has ended. This isn't mythology, it's an ecological calendar refined over 60,000 years of unbroken observation. The sophistication of this system becomes clear when you realize the emu isn't just a symbol, it's a map. In New South Wales, a sandstone rock carving of an emu aligns perfectly with the celestial version during its annual descent. At this moment, real-life emus below are nesting, their behavior synchronized with their starry counterpart. The same pattern repeats with the shark constellation Batum, which appears when monsoon rains lure sharks into shallow waters, and the stingray Walu, whose rising marks the arrival of wet season winds. Every constellation is a practical guide, linking celestial movements to tides, migrations, and harvests with pinpoint accuracy. Oral traditions preserve this knowledge with astonishing precision. Songline's mnemonic pathways of music and story encode navigation routes across vast distances, with each verse corresponding to landmarks and star positions. A single song might traverse hundreds of miles, its verses acting as turn-by-turn directions under specific constellations. When researchers compared these songs with modern star maps, they found the correlations weren't just poetic. They were mathematically precise, preserving orbital data for generations without a single written word. What's truly humbling is the timescale. Aboriginal astronomy predates Stonehenge by 50 millennia, the pyramids by 55. Their stories describe volcanic eruptions that occurred 40,000 years ago, preserved in lore about fire beings in the sky. When they speak of a time when the Southern Cross appeared differently, modern astrophysics confirms it. Due to Earth's wobble, that constellation's orientation has shifted exactly as oral histories describe. Even more striking are accounts of variable stars like Betelgeuse, whose dimming and brightening cycles were noted long before telescopes existed. This isn't just stargazing, it's a worldview where land, sky, and story are inseparable. At Wurdi Yuang, a stone arrangement in Victoria mirrors the setting positions of solstice suns, while the Borong people of the Malay region named stars after local flora and fauna, creating a cosmic ecosystem. The difference between Western and Aboriginal astronomy isn't just in the patterns they saw, but in why they looked. For the Greeks, constellations were heroes frozen in time. For indigenous Australians, they're alive, breathing entities, as dynamic as the landscape they govern. The lesson here isn't just about the past. In an era of light pollution and satellite constellations, Aboriginal elders warn that losing sight of these star stories means losing more than myth. It's severing a thread that connects humanity to the rhythms of the earth. When they say the emu's position dictates when to burn grasslands to prevent wildfires, or that the Pleiades rising signals the arrival of winter bees, they're offering something modern science is only now rediscovering, that the stars aren't just objects to study. They're partners in survival, whispering secrets to those willing to listen across generations. Polynesian navigators didn't just sail, they danced with the stars. Unlike European explorers who relied on compasses and later sextants, the wayfinders of the Pacific developed a system so intuitive yet precise that it defies modern logic. Their star compass, known as the Cape Huwetu, wasn't a physical tool but a mental map dividing the horizon into 32 directional houses, each anchored by a rising or setting star. When the sun dipped below the waves, they'd identify key stars like Hoculaire Arcturus or Ki Alii Okona I Kalua Southern Cross, not just as points of light but as moving guides whose positions shifted with the seasons. A master navigator could stand on a rocking outrigger canoe, feel the swell patterns against his feet, and correct his course by the angle of a single star's ascent, all without a single written chart. Half a world away, the Vikings faced a different challenge, navigating the North Atlantic's endless summer daylight where stars vanished for months. Their solution, the mysterious sun compass, a wooden disc with a central gnomon that cast shadows even under the midnight sun. Recent discoveries like the Unatok artifact reveal these devices were more than crude sundials. By aligning notched edges with the sun's shadow at specific latitudes, Norse sailors could maintain course despite fog or overcast skies. Some sagas even mention a sunstone, possibly calcite or cordierite crystals, that polarized sunlight to locate the sun's position through clouds. When combined with their deep knowledge of wave patterns, bird migrations, and even the color of seawater, these tools transformed the open ocean into a familiar highway. What's astonishing is how both cultures independently cracked the same cosmic code. Polynesians timed voyages by the zenith star. When a specific star like Sirius passed directly overhead, they knew they'd reached the latitude of Tahiti. Vikings, meanwhile, used Polaris's fixed position to gauge their north-south axis, dubbing it Lathos Jona, the guiding star. Neither had contact with the other, yet both developed systems where the heavens weren't just observed but deeply conversed with. The Pacific's vast emptiness and the Atlantic's brutal storms demanded nothing less than total synergy between Navigator and Cosmos. The real test of these ancient techniques came in modern times. In 1976, the Hokulea, a replica Polynesian double-hulled canoe, sailed from Hawaii to Tahiti using only traditional methods: no GPS, no sextants, just the stars, waves, and a navigator memorizing hundreds of celestial markers. Against all odds, they arrived within miles of their target. Similarly, Viking ship reconstructions like the Saga Oseberg successfully crossed the North Atlantic using sun compass replicas, proving these weren't myths but precision instruments. Yet the most profound lesson lies in their shared philosophy. Both cultures saw navigation as a sacred dialogue with nature. Polynesian chants called the stars kupuna, ancestors guiding their descendants. Norse poetry described the sun compass as a gift from the god Odin, who stole the secrets of the heavens. This wasn't just practicality, it was reverence, a recognition that crossing oceans required more than skill. It demanded humility before the vastness of the sky and sea, a partnership between human ingenuity and cosmic wisdom that modern technology, for all its power, can never fully replicate. In the shadow of ziggurats and pyramids, where celestial knowledge was often guarded by male priests, one woman's voice rings clear across 43 centuries. Enheduanna, the high priestess of wasn't just the daughter of Sargon the Great, she was astronomy's first named author. Her hymns to the moon god Nanna aren't merely poetry. They're precise observations of lunar phases, written in cuneiform around 2300 BC. When she describes the moon's horned crown or its hidden face, she's documenting cycles that Babylonian astronomers would later formalize into predictive tables. This wasn't incidental symbolism, it was science disguised as devotion, proving that temple priestesses were among humanity's earliest astrophysicists. Egypt's sands whisper similar stories. Hatshepsut, the female pharaoh who ruled 1500 years after Enheduanna, didn't just build monuments, she engineered them as celestial mirrors. Her mortuary temple at Deir el-Bahari aligns with the winter solstice sunrise, flooding the innermost sanctuary with light that would illuminate statues of the gods. But the real revelation lies in her expedition to Punt, meticulously recorded on temple walls. The stela includes what scholars believe are stellar navigation charts, suggesting Hatshepsut's sailors used star positions to cross the Red Sea. For a woman often remembered for her political savvy, her astronomical legacy remains startlingly overlooked. Then there's Aglaonike of Thessaly, the witch who could draw down the moon. Ancient Greek texts dismiss her as a sorceress, but modern historians recognize her as Europe's first known female astronomer. Living around 200 BCE, she mastered the Saros cycle, the same Babylonian eclipse prediction method, so thoroughly that her ability to forecast lunar eclipses seemed supernatural to contemporaries. Plato even referenced her in his dialogues, though through the condescending lens of his era. she knew the reason for the moon's disappearance better than any barbarian. No discussion of women in ancient astronomy would be complete without Hypatia of Alexandria, the mathematician and philosopher whose murder in 415 CE symbolizes the violent suppression of intellectual freedom. While her father Theon refined Ptolemy's star catalogues, Hypatia surpassed him, inventing the astrolabe's precursor and writing commentaries on planetary motion that influenced medieval scholars. Her lectures at the Mauseon attracted students from across the Mediterranean, blending Neoplatonist philosophy with rigorous celestial mechanics. The tragedy isn't just her brutal death at the hands of a Christian mob, it's how her erasure foreshadowed centuries of women being written out of scientific history. These women's achievements become even more remarkable when you consider the barriers they faced. The Greek astronomer Timacharis worked alongside his wife Theno, yet only his name survives in star catalogues. Chinese court astronomers like Wang Zhenyi in the 18th century had to publish under male pseudonyms to be taken seriously. Even in Mesoamerica, where Spanish chroniclers recorded male astronomers' predictions, the sacred books burned by missionaries likely included contributions from female scribes and calendar keepers now lost to time. What's often missed is how their approaches differed from male contemporaries. Enheduanna's lunar hymns connect celestial patterns to agricultural cycles, grounding astronomy in daily life. Hatshepsut's temple alignments merge politics with cosmic symbolism, using the sun's path to legitimize her unprecedented rule. Hypatia's teaching fused math with ethics, insisting that understanding the heavens demanded moral clarity. Their legacy isn't just in what they discovered, but in how they framed astronomy not as abstract theory, but as knowledge intertwined with community, spirituality, and power. The real crime of history isn't that these women were rare, it's that their stories were systematically erased. For every Hypatia, there were dozens whose names we'll never know. The anonymous Mayan women who painted eclipse tables in Dresden Codex margins, the Sumerian priestesses who tracked Venus for temple rituals, the Inuit elders who passed down star-based navigation songs. Their absence from textbooks says more about our biases than their contributions. When we restore their place in astronomy's origin story, we don't just correct the record, we rediscover a richer, messier, and far more inclusive history of human curiosity reaching for the stars. Imagine stepping outside on a clear night in ancient Babylon, where the sky wasn't just dotted with stars, it blazed with them. The Milky Way arched overhead like a river of crushed diamonds, so bright it cast faint shadows on the ground. Orion's belt didn't just feature 3 stars, it was embedded in a glittering tapestry of hundreds more, all visible to the naked eye. This wasn't a rare celestial event. It was the everyday reality for our ancestors. Today, that same sky is a ghost of its former self, drowned in the orange glow of streetlights and neon signs. Over 80% of the world's population now lives under light-polluted skies, where fewer than 50 stars are typically visible. For millennia, humanity's greatest library of knowledge was written in the stars, and we've accidentally closed the book. The loss isn't just aesthetic, it's cultural. Ancient astronomers like Ptolemy or the Maya skywatchers didn't need telescopes because their night skies were pristine laboratories. The Andromeda Galaxy, a faint smudge to modern city dwellers, was so obvious to Persian astronomers that they catalogued it as the little cloud over 1,000 years ago. When the Greek poet Aratus described the constellation Draco as coiled in splendor, he wasn't exaggerating without light pollution. Draco's tail was a vivid chain of stars winding through the zenith. Even the zodiac's lesser constellations, like Cancer or Capricornus, shone clearly enough to inspire myths and guide navigation. Today, these patterns are erased from urban skylines, leaving only the brightest stars as lonely survivors. But here's what's truly startling. The change happened faster than we realize. As recently as the 19th century, gas lamps in cities like Paris or London were so dim that astronomers could still study the heavens from their rooftops. The Harvard College Observatory, where Edward Pickering's computers mapped stellar spectra in the 1880s, was just blocks from downtown Cambridge. Now, those same skies are obliterated by LEDs and high rises. Satellite images reveal that global light pollution increases by about 2% annually, with some regions, like rapidly developing areas of Asia, seeing the night sky brightness double in a single decade. The stars that guided Polynesian navigators or Babylonian farmers are vanishing at a pace that would have horrified our ancestors. The consequences ripple far beyond nostalgia. Light pollution disrupts ecosystems, confusing migratory birds that rely on starlight and decimating firefly populations. For humans, excessive artificial light at night is linked to sleep disorders and even increased cancer risks. Yet the most profound loss might be philosophical. Ancient cultures saw the cosmos as a mirror, whether it was the Egyptian belief that the Nile mirrored the Milky Way or the Navajo concept of the starway connecting earth and sky. When we lose the stars, we're not just losing light, we're severing a connection that shaped art, religion, and science for thousands of years. There are flickers of hope. Dark sky preserves, like Chile's Atacama Desert or Namibia's Namibrand, offer glimpses of the pre-industrial heavens. Modern apps can simulate pristine skies on smartphones, and communities are adopting shielded lighting to reduce glare. But the real challenge isn't technical, it's remembering what we've lost. The next time you look up and see only a handful of stars, remember, you're not just seeing less. You're seeing a sky that's been edited, stripped of its depth and context. The cosmos our ancestors knew wasn't just brighter, it was alive with meaning, a shared inheritance we've only just begun to miss. Beneath the dense jungles of Guatemala, where vines and centuries of soil had concealed entire cities, a revolution in archaeology was quietly unfolding, not with shovels but with lasers. In 2018, LiDAR surveys pierced the forest canopy, revealing 60,000 previously unknown Mayan structures, pyramids aligned to solstice sunrises, causeways stretching toward Venus's setting points, and reservoirs positioned using celestial markers. These weren't random constructions, they were fragments of a vast cosmic blueprint, invisible to the naked eye but unmistakable from the air. The same technology has exposed similar secrets worldwide, from Cambodia's Angkor Wat, where temples mirror Draco's stars, to the Amazon's sprawling geometric earthworks, aligned to the winter solstice with eerie precision. Suddenly, we're not just studying ancient astronomy, we're seeing it in 3 dimensions, at a scale our ancestors could never have imagined. Meanwhile, astrophysicists are turning back time with software like Stellarium and Sky Safari, which can recreate the night sky as it appeared over Babylon in 3000 BCE or above Choco Canyon in 1100 CE. When researchers input the date of the Battle of Marathon in 490 BCE, they found Herodotus's claim about a waning moon was astronomically accurate, a detail that once seemed like poetic license. These digital time machines reveal how celestial events shaped history. The supernova of 1054, recorded by Chinese and Puebloan observers alike, blazed brighter than Venus for weeks, leaving its remnant as the Crab Nebula. Even the Star of Bethlehem, long debated by theologians, now has a plausible astronomical explanation, a rare conjunction of Jupiter and Venus in 2 BC that would have shone with startling brilliance. But the real game changer is how these tools democratize ancient wisdom. Apps like Star Walk now overlay Babylonian constellation boundaries on modern skies. while augmented reality lets you point your phone at the heavens and see how the Inca viewed the Milky Way as a celestial river. Archaeologists using 3D modeling have reconstructed the acoustics of Stonehenge, discovering how sound waves amplified solstice rituals. And when linguists fed Mayan glyphs into AI, they cracked eclipse prediction codes that had baffled scholars for decades. Turns out, the Maya tracked lunar cycles down to minutes using math we'd considered too advanced for their time. The irony is delicious. Our most cutting-edge tech is resurrecting humanity's oldest science. Drones map Nazca lines that align with star risings, while spectrographs analyze Egyptian temple paints to reveal pigments mixed with meteoritic iron, literally star metal. Perhaps the most poignant discovery came when astronomers compared ancient Chinese star maps with modern catalogs and realized their guest stars included supernovae whose remnants we can still observe today. These aren't just data points, they're messages across millennia, proving that the sky our ancestors studied is the same one we're exploring with satellites and rovers. The tools have changed, but the wonder remains a thread of curiosity stretching from the first stargazer who noticed a wandering planet to the researchers who now decode their legacy with lasers and algorithms. The wisdom of ancient astronomers isn't just a relic of the past, it's a living toolkit for modern science. Take Stonehenge. Today, educators use its alignments to teach students how celestial mechanics governed Neolithic life. By tracing the path of solstice sunlight through its towering stones, they demonstrate principles of axial tilt and orbital motion in a way no textbook could match. But the real power lies in the lesson behind the lesson. These structures weren't built by people who saw the sky as separate from daily existence. They were crafted by cultures that wove astronomy into agriculture, architecture, and art. In an age where science often feels siloed from spirituality, their integrated worldview offers a radical alternative, one where data and wonder aren't rivals but partners. Consider how Polynesian navigators memorized wave patterns and star paths as interconnected systems. Modern oceanographers now collaborate with surviving wayfinders to refine climate models, blending indigenous knowledge with satellite data to track shifting currents. The result, more accurate predictions of El Niño events, proving that ancient techniques can sharpen cutting-edge science. Similarly, archaeologists studying Maya eclipse records have uncovered evidence of solar storms that could inform today's space weather forecasts, potentially protecting our power grids from catastrophic blackouts. The past isn't just informative, it's practically prescriptive, yet the most profound legacy might be philosophical. The Dogon's reverence for Sirius or the Inca's belief in celestial kinship reflects a mindset we've largely abandoned, the universe as a conscious participant in human life. While we've gained precision with telescopes and algorithms, we've lost the visceral connection that turned stars into storytellers. Some modern initiatives are bridging this gap. Dark sky preserves, modeled after indigenous stargazing practices, reintroduce urban dwellers to the Milky Way splendor, while planetariums incorporate Aboriginal songlines into their shows, merging astrophysics with oral tradition. This isn't about nostalgia, it's about reintegration. When a physicist cites Babylon's eclipse tablets to calibrate lunar recession rates, or a biologist studies how Neolithic farmers timed plantings by the Pleiades, they're acknowledging that science thrives when it honors its roots. The ancients remind us that curiosity alone isn't enough. It must be paired with reverence. Their stone circles and star charts weren't just tools. They were invitations to look up, to wonder, and to remember that we're part of something far grander than ourselves. In rediscovering their legacy, we might just find a way to heal the rift between our equations and our